Welcome to your final briefing, junior flight engineers. You have studied the theoretical physics of quadcopters and the hardware required for stable flight. Now we apply those mechanics to real-world engineering crises. After a massive wildfire, the landscape is often stripped of its root systems. The terrain becomes too steep and unstable for human planting crews to navigate, leaving thousands of acres of forest unable to recover on their own. To solve this, environmental engineers deploy heavy-lift multi-rotor drones. These aircraft operate in synchronized autonomous swarms to execute rapid aerial reforestation. This protocol begins with a 3D map. Scout drones use LiDAR and cameras to identify optimal soil microsites for seeds. Then, heavy-lift drones fly pre-programmed paths, firing biodegradable seed capsules into the soil, planting up to 180 trees per minute. Aerospace engineering provides the speed and precision necessary to restore an ecosystem, turning a collection of motors and sensors into a tool for planetary recovery. In regions like Uttar Pradesh, India, geography creates a different kind of barrier. Dense traffic and mountain ranges can cut off rural clinics from the rapid transport required for time-sensitive medical supplies. Fixed-wing hybrid drones solve this by bypassing ground obstacles entirely, delivering vaccines and blood transfusions directly from the air. To deliver this cargo safely, the drone must maintain a stable flight path through unpredictable mountain winds without constant human intervention. The software maintaining this stability is the extended Kalman filter. It acts as a mathematical judge that fuses these distinct inputs. It uses rapid data from the IMU for immediate balance, then cross-references that data with periodic GPS pings to correct any accumulating drift. This sensor fusion allows the drone to navigate complex airways autonomously, delivering medical cargo in minutes instead of the hours required for ground transport. The mathematical logic inside a flight controller provides the reliability needed to overcome physical barriers and save human lives. While Earth presents its own challenges, the ultimate test of an engineer's ingenuity lies in adapting flight to an entirely alien environment, Mars. On Mars, the atmosphere is roughly 1% as dense as Earth's. It is a cold, thin environment composed mostly of carbon dioxide. At this density, a standard drone's propellers would spin uselessly. The blades would simply fail to displace enough air molecules to generate upward lift. To achieve flight in these conditions, NASA engineers developed the Ingenuity Mars helicopter. Because the air is so thin, the helicopter requires a massive aerodynamic surface area. This technical comparison shows the scale. Ingenuity uses two coaxial rotors stacked together, each spanning 1.2 meters. These rotors must spin between 2,400 and 2,800 RPM in opposite directions. This speed allows the blades to bite into the thin CO2, while the coaxial layout cancels out rotational torque. The blades themselves are forged from Techstream carbon fiber, an ultra-light, rigid composite designed to maintain its shape and efficiency at the supersonic tip speeds required on Mars. Tucked beneath Ingenuity's solar panel was a piece of muslin fabric from the original 1903 Wright Flyer, marking the connection between early aviation and interplanetary robotics. The success of Ingenuity proves that the laws of physics are universal. When an engineer understands the environment, they can modify the hardware to master it. From reforestation and medical logistics to the surface of Mars, drone technology has moved from a theoretical experiment to a global solution for complex problems. On a workbench, a quadcopter consists of a carbon fiber frame, copper wound motors, and silicon circuitry. The engineering within the flight controller, the mathematical physics of the PID loop, and the precise timing of the ESCs is what transforms these materials into an acrobatic machine. These same principles invite you to solve new design challenges. Adapting the propeller pitch and motor torque used on Earth could allow for flight through the crushing gravity of a gas giant like Jupiter, or permit a craft to dive from the sky and operate as a submarine. You understand the mechanics and the code. You are the architect of these systems. What will you build next?